All right, let's take a look at a problem that tackles the conservation of momentum equation. So I'll do a couple practice problems, but just to give you a taste of what they're like and let you kind of try this here. So here we have a boater that's stepping on a boat, and this is a common thing if you go to the water, you spend time in the lake in the summer, and you go to step off the boat, so you step to the right, the boat is forced to go backwards, right? And the boat goes backwards. When we think about why does the boat go backwards, well, it's this conservation of momentum. When you're standing still on the boat, the total momentum of you in the system is 0. And so that means if you move forward, you've gained a positive momentum. If we call it to the right positive, the boat has to have a momentum that's equal and opposite to you so that the total momentum of the system, and when I say system, I'm defining everything that's involved in the situation. So that would be you, and the boat would be the system. The total momentum needs to stay at 0. All right, so let's take a look at this, and I'm going to shrink this here so we can start working on this problem. It says we have a 76 kilogram boater, so I'll do my table of knowns. But my knowns are the mass of the boater, we'll call this BR for boater, and his mass is 76 kilograms. We know the mass of the boater initially is 0 meters per second. We've got the mass of the boat, so we'll do BO for boat, and that is 45 kilograms. And we know the mass of the, we know the velocity of the boat initially. So boat initial is 0 meters per second. And then in our situation, so if we think of our equation for momentum, right, I know that mv1 plus m2v2, okay, initially, so here's my initial situation. So in my initial situation, both of the velocities are 0. Right? Velocity of the boater is 0. The velocity of the boat is 0. So my initial velocity, or my initial momentum, sorry, right here is 0. So that has to be equal to m1 v1 plus m2 v2. And this is after. So after the situation, we know the boater moves to the right, which we'll call positive. So let's call this positive, with a velocity of 2.5 meters per second. So we'll call him object 1 here. So this is, the boater has a mass of 76. So we've got 76 times 2.5. And since we've already defined to the right as positive, we know the boat's going to move to the left. So we know this is going to be a minus here. So it's going to be minus the mass of the boat times the velocity of the boat, which is our unknown. Okay, well, this all equals 0. So then I can add this 45 times v to the other side. We end up with an equation that looks like this. 45 times v equals 76, which is the mass of the boater, times 2.5, which is his velocity. And we can solve this for v. And when we solve this for v, we get an answer of negative 4.2 meters per second. 4.2 being negative tells us that it is in the opposite direction that we decided was positive, which was to the right. So this is 4.2 meters per second. So I'm going to get rid of the negative sign and make this to the left. Okay, so this is a sample of a conservation of momentum problem. Let's do another one. So here's a situation where you have a situation where the objects stick together after the collision. So here we read this problem. So we have a luxury sedan stopped at a traffic light and is struck from the rear by another car. The cars become entangled as a result of a collision. And then it says if the compact car were moving at a velocity of 22 meters per second. So the situation kind of looks like this. We're going to take a bird's eye view so we can kind of draw this out. So here is car 1. The compact car is moving north 22.0 meters per second, and then car 2 is here, and this car had a speed of 0 meters per second. They collide, and they stick together, and we know they're going to continue moving this way, but we don't know what the speed is going to be after the collision, so we need to find that. So here's a chance to use my inelastic collision equation. So we've got the initial velocity, the initial momentum of the two cars. If this, we'll make this car 1, we'll make this the moving car. So this is 975 is the mass, right? And the velocity of that car is 22.0. The other car has a mass of 1850 times 0, right? It had no velocity. And so we're asked to find the moment, or the velocity after the collision. So we know their combined mass, because they stick together after the collision, is going to be (1850 plus 975 times VF). So now to solve this becomes 0, so we can get rid of this. And then we can multiply here and get this number, and then divide by 1850 plus 975. And we get a VF of, and this 7.59. Since our answer comes out positive, that tells us that it's in the same direction of our original velocity, which was to the north. Okay, so that's it. That's how you do momentum problems as they present themselves in Unit 6.